Hello and welcome to lesson number 2, functions. So, in the previous lesson we talked about sets. Now we're going to talk about functions. I did mention functions and relations in the last lesson also, but now we're going to dive deeper into functions. Specifically, we're only going to really be talking about single variable functions. That means functions that have only one variable as an input. However, note that there are other types of functions that can have multiple variables as inputs. So for now, we're first going to go over the notation and then we're going to go over specifics of certain functions. So a function, as you will no doubt know from your O-level times, is written as some symbol and the input around it usually. In this case, f of x is the function f, which takes an input x, and on the right side we equate this to some relationship between x and fx. So if I say that this is x squared, then that means that f of 1 would be 1 squared would be 1, and f of 2, which is when we input 2 instead of x, will be 2 squared or 4. And similarly f of 3, we'll just illustrate a little more. F of 3 is 3 squared, which is 9. If instead I define fx as, let's say, fx equals 2x plus 3, let's say, a simple function. So in this case, f1 would be 2 times 1 plus 3. So because here instead of x I have to substitute 1, which then gives us 5. And similarly f2 would be 2 times 2 plus 3, which will give us 7. Similarly, f of 3 would be 2 times 3 plus 3, which is 9. So this is the relationship, and this is how we notate functions. You can of course use any symbol you want. It doesn't have to be f. We tend to use f as the simplest function because that is, f for function, I suppose. But commonly we use other symbols also. Gx is a very common one. Hx is the next common one. Sometimes people write px and qx. And of course, any other symbol can be written as a function. For example, there's something called the Riemann-Zeta function. It's not the symbol. It's like this. It's a function of x. There's something called the gamma function. It's a function of x. It takes an input, it does something to it, it produces an output. So, just if you ever see this notation, some symbol, usually capital or simple letter, followed by a variable symbol inside of brackets, it is a function. Usually we don't use any other notation for functions. Sometimes there are other things that we use for functions. For example, we might just write a different variable on the left side. Instead of f of x, we might say y equals x squared. This is not exactly a function. This is representing a graph of a function, saying that if we plot this function, this relationship on a graph, what would it be? Usually we don't tend to use y. Usually we tend to represent a function with fx rather than a different symbol y. But this is also common, and you would no doubt use this notation when you want to draw a graph. For example, y equals mx plus c is a line, and but if we instead have fx equals mx plus c, it's the same exact thing, except now we're treating it like it's a function. This is more geometric, this is more functional, more in the realm of functions. So now that we've introduced functions and how we write them, it's really quite simple. Now let's go into some specifics of certain functions. So for us, this is a single value function where we have only one input. I'll quickly go over how we write multi-value functions. Really quite simple. We again still write f or the symbol for our function, but now we put two inputs. Let's say xy. fxy is x squared plus 2 xy plus y, let's say. This is a multi-value function. That's it. That's really it. So, but the only thing here, for these functions, you need to input two values. Let's say I input 1, 2. This means that instead of x I substitute 1, instead of y I substitute 2. So the value of this function's output at 1, 2 would be, for x is 1, so 1 squared plus 2 times, again x is 1, y is 2 plus y is 2. Y is 2. So this would be 1 plus 2 times 2, which is 4, plus 2, which is 6. So 6 plus 1 would be 7. So f of 1, 2 would be 7. It's really not all that big of a jump, but we do not have these multi-valued functions in our syllabus at least, so we will not consider them too much. But I just have to tell you how we would write them and calculate their values. So within these functions, there are certain things that we define. For a function, let's say fx, we define something called the domain D, the domain, something called the range, and something called the codomain. These three are three values, well, not exactly values, they are really sets that we define, or if we don't define them, we at least can find them for a given function f of x. So a function takes certain inputs and makes it into a certain set of outputs. The set of all possible inputs of a function, the inputs of a function, is what we call the domain. The domain is the set of all valid inputs of the function. All the outputs of the function corresponding to that set of inputs is what we call the range. So that's the range of the function. And the codomain is the set of all theoretically possible outputs. So the codomain and range are not necessarily the same thing. The codomain just says, okay, if we take these inputs, what are the possible outputs that we could hit? And then the range tells you the actual subset of those possible outputs that are actually hit. So let's take an example and I'll explain to you what each of these is in that example. Let's say fx is x squared, a simple function like this. For this thing, I'll say that x can be any element of the real numbers. So if x is any element of the real numbers, that means the real numbers are the set of possible inputs for fx. So in this case, the domain we can start with, the domain is the real numbers, because I'm allowing any real number to be input into the function fx. Then, considering the outputs, the possible outputs, a real number squared is going to stay within the real numbers. So the codomain or the set that contains all the possible outputs that we could have produced is also the real numbers, because a real number squared is still a real number. However, note that when you square a real number, the only possible values are either 0 or a positive number, because a negative number times a negative number is a positive number times a positive number is a positive number, and 0 times 0 is 0. So the actual range of values that we can hit is a subset of the real numbers. It is actually the real positive numbers including 0. If I write this in the notation of a range, it is the numbers including 0 up to infinity, up to positive infinity, and not including positive infinity. I do not think I have introduced this notation. The square bracket indicates inclusive, is inclusive. The curly brackets like this indicate exclusive, inclusive. So what I mean by this, I believe this has been taught in O-level times, but I will teach it anyway. The square bracket indicates that within a certain range, the lower or upper bound is included into the range. So if you take a number line, let's say for this example function of fx, for fx, the point 0 is a valid output. So I'm going to color it in. I believe this has also been taught in O-level times, so I shouldn't need to teach this, but I will teach it anyway. the point 0 is a valid output, and then all the values above 0 are also valid, so they are also colored in on the number line like this. So this is what we mean when I say the range is 0 inclusive up to infinity exclusive. And it should also be noted that infinity is always excluded when we are talking about the range. Any range of values, infinities are excluded. Negative infinity is excluded, infinity is excluded. So that is the definition, and this is the range of fx. This is the range of fx. It's the set of all possible outputs of fx given the domain of fx that we introduced. We introduced fx element where x is element of the real numbers. If instead of this, if I define gx, when I say gx is also x squared, but for x element of the positive integers, now we have a different situation. If we consider x element of the positive integers, then the domain of this function, the domain is the positive integers, because that's the only inputs that we could introduce. Now the codomain of this function would be the integers, because when we square an integer we should get another integer. We cannot square a non-integer, we cannot square an integer and get a non-integer. So therefore the codomain must be the integers. And the actual range that we have, the range we have is the positive integers. Why? Well, let's just see what happens when we square these numbers. If I take the domain of positive integers, this is the set 1, 2, 3, 4, 5 and so on. If I convert this into the range, what I get? 1 squared maps to 1. 2 squared maps to, sorry, that arrow is too long. 2 squared maps to 4. 3 squared maps to 9. 4 squared maps to 16. And 5 squared maps to 25 and so on. All of these are elements of the positive integers. So therefore the range is a set of positive integers. The range is also a subset of the positive integers as well, because we're only considering these values that are perfect squares of positive integers. So you could say that the range is not exactly the positive integers, it is actually this, and some people do that also. You could say the range is actually not the positive integers, the range is all of these numbers. The range is this set of possible outputs. So that's the domain, range and codomain. Generally in our A level we do not think about the codomain too much. The codomain is important if you want to think about onto-ness of a function. Onto-ness of a function means, is every possible output covered by the function? Does the function hit every single point along the output of the function? In this case, for the y equals fx, where fx is x squared, this function is not an onto function because it misses certain points. For example, the point -1 is not hit by the function fx for its domain in the real numbers. Why? Because it simply cannot be done. There's no real number x that we can input such that fx outputs -1. Therefore, -1 is not in the range of fx, and therefore the range of fx does not cover the entire codomain, and therefore fx is not an onto function. A function, however, let's say hx. A function hx, such as just x, or let's say 2x plus 1. If hx is the function 2x plus 1, and we allow its range, the range of fx to be, the domain of fx, if we allow the domain of fx to be the real numbers, as in we say that x is an element of the real numbers, then if we plot this graph, we will clearly see that the range of this function is also the real numbers, and considering this function, the codomain of this function, codomain would also be the real numbers. So because the range and codomain are exactly equal to each other, we can say this function is an onto function. We can say hx is an onto function. This onto function is just a word, and it means that every possible output of hx is hit by hx. There is no output we can get from hx that is not findable. If we draw this graph of hx, it will be something like this. It will be a line like this. So here this is 1, and you'll notice instead of putting y, I'll put hx and x. Every single possible value of hx is found. Hx can be any real number, and therefore hx is an onto function, because the range of hx is the same as the codomain of hx. Since we've just covered onto functions, let's segue into the next subject here, which I'm going to talk about, which is the inverse function. So if we have a function f of x which maps x onto, let's say, y, or let's use set notation for this thing. Let's say f maps the set A onto the set B. It takes all the values in A, all the elements in A, maps those elements onto B. What I mean by the inverse function is the function which is usually written as f inverse something like this, which maps all the values of B back onto A. So an inverse function should have these properties. If you have an inverse function f inverse of x, then we should have the property that f of f inverse of x is equal to x, and f inverse of fx is also equal to x. This should be true, both of these should be true for all I kind of merged those two words together, for all values of x. It should work not only for a few values, but for every single possible value of x. This should be the case. This is the only real criterion, the fact that the inverse function should undo whatever the function is doing. These two functions should be a pair which undo each other, which is basically what these two statements say. Fx undoes f inverse of x, and f inverse of x undoes fx. An example of these function like this would be, let's say fx. We'll define an fx and we'll find its inverse. Let's say fx is that function from earlier, 2x plus 3. Alright, then f inverse of x would be x minus 3 divided by 2. And I'll explain how we find inverse functions, and we find if inverse functions exist, if they're valid, and that in a moment. But let me just show you what happens if you do some value here. Let's try f of 2. F of 2 is 2 times substituting x as 2 plus 3, which is 4 plus 3, which is 7. So f of 2 is 7. Then if I take f inverse of that value, or I'll just say f inverse of f of 2, this is f inverse of 7, because f of 2, the thing I'm substituting as the input into the second function, is this output that we just found, 7. So this is f inverse of 7, which is 7 minus 3. I'll put a bracket around the 7 because the 7 was substituted, minus 3 divided by 2, which is 4 divided by 2, which is 2. And this number is exactly what we started with. It is the input of the function. So here we can clearly see f inverse of f of 2 is 2. We have that property. If we do it the other way, if I say we take the f of f inverse of some number. Let's say we take the f inverse of 5, right? Now let's calculate what this is. To find this thing, first we find the inside function. So we have f of, and then on the inside, f inverse of 5 is 5 minus 3 divided by 2. We're substituting into x the value of 5. So here, if we simplify this, we get, this is f of 5 minus 3 is 2, 2 divided by 2 is 1. So this is f of 1. What is f of 1 now? Well, f of x is 2x plus 3. So f of 1 will be 2 times 1 plus 3, which is 2 plus 3, which is 5. We have that property as well. We have that f of f inverse of 5 is 5, so f of f inverse of x could be x. And we have the property that f inverse of fx also gives us that same input. So in this case, if you want to really find the inverse function, all you have to do is swap the variables. You have to essentially say, what function, if I substitute fx into, will I get x back? And to do this, one of the easiest ways to do it is to simply write it in as variable format. Say, we have the function, let's just take the one we just did. Instead of saying fx is 2x plus 3, I'll just say y is 2x plus 3. And now, I'll try to find a formula for x in terms of y, which means I want x on the left, and I want something like x equals something containing y inside of it. So if we do this for this simple equation, the first thing to do to get x all by itself would be to take this 3 to this side. So we have, I'm going to swap the two sides also and say 2x is equal to y minus 3. Now all I need to do to get x all in its own is to simply divide by 2. So I get x equals y minus 3 divided by 2. That's our inverse function. So now if I want to write this in a it's in a function of x format, I actually need to swap these two variables, because here what I was trying to do is find the input in terms of the output. No, so what I actually found here is that x equals fx minus 3 divided by 2. What I want to find is that f inverse of x is x minus 3 divided by 2, because this x is not a real object, it's just a variable, it's just the input of the function. So I can write this upward equation as x is the f inverse of fx. It's a little kind of cheating, but is fx minus 3 divided by 2, and therefore this and this are the same thing, which means it doesn't really matter what I represent by them. So I can just say f inverse, I'll replace the fx with simply x, saying that that's my input, and x minus 3 divided by 2. Whatever method suits you, it doesn't really matter how you get the inverse function, so long as like you could substitute the variable, you could try some other rearrangement method, you can get it. So this is actually a function that happens to work. It happens to have an inverse function which is also a function. I'll tell you about functions that don't have inverse functions also, but for right now, this is a function that works. And one of the reasons, the main reason it works, is because this function is 1, 2, 1, and it is onto. What I mean by this is that one input of x corresponds to one output of y, and more importantly, one output of y can only be found by one input of x. The function is also onto, which means for every possible x there is a correspondent y, and every possible y there is a correspondent x, covering the entire set of possible outputs and inputs. So this means there's no value we cannot substitute into this function or its inverse that will not give us an answer. So this is an invertible function because it is one-to-one and onto. In fact, we can say a function is invertible if it is one-to-one and it is onto. So I'll show you now an example of a function that is not invertible exactly. The function f of x equals x squared. If you take this function f of x equals x squared, you might think, oh, that's easy, f inverse of x should be the square root of x, right? Because the square root of the square is the number itself. No, it's not. It's not. I'll show you why it's not, and I'll show you why you might think that it is. So if we take f of 5 is 25 because that's just x squared. So then f inverse of 25 would be the square root of 25, which is 5. This is alright, it works. However, try f of negative 5. F of negative 5 is still 25 because negative 5 squared is 25. But now when we try f inverse of 25 this time, we still get 5. We do not get negative 5 back. So the equation f inverse of fx not exactly equals x for all x. It works for some x. It works specifically for all the positive x including 0. It does not work for any of the negative x because the negative x is mapped onto the positive x, and that happens because this function is not one-to-one. There are two possible inputs that lead to a single output. Well, for 0 there's only one, but for all the other numbers there's two numbers that lead to the same output. Negative 5 and 5 both map to 25. So this is not a one-to-one function. This is in fact a many-to-one function, which means a proper inverse of this function does not exist. This is not in fact the inverse function. If you really want the function that gives you the answers, it would have to be plus or minus the square root of x, which is not a function because for a single input there's multiple outputs. So we have a problem. We cannot find a proper inverse function of this fx. And well, that's to be expected. Some functions are simply not invertible. So in this case, we do not have the proper inverse function, which means if you want an inverse function, you need to add some additional non-functional properties to it. That's what this plus minus is. So it's an improper inverse function, which means it's not actually a function, because remember, a function should only have one output for one corresponding input. This one happens to have two. F inverse x is plus or minus square root of x. We cannot really do much about this. This is simply the non-perfect inverse function, but we can define this as the inverse function, or we can even define this as the inverse function and say that this inverse function is not actually a function, it's not perfect. It will give you some values, but there's some additional work that you have to do to figure out which value you want. This is, for example, the reason why the same issue is why the quadratic formula has two answers, two roots. We cannot find a proper inverse formula for the quadratic formula. The quadratic formula, if we take fx equals ax squared plus bx plus c, and we want to find when fx equals 0 or when fx equals some other constant k. If we want to find fx equals k, right? And we want the inverse function of this. Well, you know, from the quadratic formula, we can find x squared plus bx plus c equal to 0. So if we want to find ax squared plus bx plus c equal to k, we take the k to this side and we say x squared plus bx plus c minus k equal to 0. Now this is the quadratic formula, a form of the quadratic formula where it's not equal to 0 anymore. Now it's equal to some other constant. but we know how to solve this equation, and if we do, we get that x equals negative b plus minus the square root of b squared minus 4a, not c now, c minus k, divided by 2a, right? So in this case, this k is actually our f of x. It's our output. So if I want to write this as an inverse function, the inverse function to the quadratic formula we showed above, this one, is in fact, f inverse of x is in fact negative b plus minus the square root of b squared minus 4a c minus x divided by 2a. This function has a plus minus in it because our forward direction function was not a one-to-one function. It was in fact, even though it was not a onto function either, because the y equals x squared plus ax squared plus bx plus c would have maximum or minimum. So it's not a onto function either, but it is also not a one-to-one function. There's two values of x that could correspond to one value of y, which is why this plus or minus exists. So if you ever see that kind of conditional or plus minus or that kind of thing, know that this function is not actually a function. So that's what an inverse function is. There are some other inverse functions which are also having their own issues. For example, the sine function, sine of x. Sine of x has an inverse function known as the sine inverse of x. But the sine inverse of x function is not a proper inverse function of sine x. The reason for this is, of course, because sine x is not a one-to-one function. If I plot sine x like this, if I plot sine of x, I can see that for a single value of y, there are multiple correspondent values of x. So, if I did make a proper sine inverse function, it would not be a function. Instead, what we do in mathematics for the sine inverse function, we define the sine inverse function only going in a certain range. We start it from negative 90 degrees or negative pi by 2 degrees and end it at positive 90 degrees or positive pi by 2 degrees. We start from negative 1, do this, go to positive 1, and within this small range we have a one-to-one correspondence of angles and sine of that angle. So this is not a proper inverse function. Because of that, sine inverse of sine of x is not necessarily equal to x. However, there is a nice property that sine of sine inverse x will be equal to x provided x is between negative 1 inclusive and 1 inclusive. This is because sine inverse of x has a domain which is only between negative 1 and 1. We will be discussing further on inverse functions later, but right now let's move on to the next topic of functions, which are composite functions. We actually saw these composite functions earlier when we wrote f inverse of fx. This essentially meant we take the output of fx and provide it as the input to f inverse of x. It doesn't have to be like this, of course. We can have two different functions. For example, if I take f of x equal to 2x plus 1 and I take g of x equal to x squared, then what I would have if I took the output of fx and substituted it into gx would be g of 2x plus 1, which means instead of x I substitute 2x plus 1. If I substitute that into here, I would then have 2x plus 1 squared. Therefore, g of f of x, which is often written without this second bracket, this bracket here, these brackets are not written and we just write it like g of f of x. This would be equal to the square of 2x plus 1, which if I expand out would be 4x squared plus 4x plus 1. So g of f of x is this. How about f of g of x? If I take the output of gx and substitute into the fx, what would I get? Well, gx is x squared. So then f of x squared is what I want to find. Taking x squared and substituting it into here, instead of x I would have to write x squared. So therefore, the function f of g of x is 2 x squared plus 1. And note that these two are not the same. They are not necessarily the same. They could potentially be the same if the two functions are the same, but they will not necessarily be the same. G of f of x is what happens when you take the output of fx and plug it as the input of gx. F of g of x is what happens when you take the output of gx and plug it into fx. Similarly, we can have many more composite functions. We can chain multiple together. For example, I could even try f of g of f of x, and we can quickly figure out what this is. This is what happens when you take the output of fx, substitute into gx, and take that output and substitute into fx again. We've already found what g of f of x is, which is this. So it's quite easy to find f of that function. It is simply that function substituted instead of x. So f of x is 2x plus 1. So f of g of f of x would be 2 times g of f of x, which is x squared plus 4x plus 1 plus 1. So then f of g of f of x would be 8x squared plus 8x plus 3. I hope we are all clear on that. I hope there's no real issues with this. Just know that we can stack functions as much as we want. We can stack functions on top of functions as many layers deep as we want. And as a conclusion, I would like to talk about some special functions. One special function is the function f of x equals 0. This is the null function. We call it the null function. Null function. It has its equivalent in different areas. Right now, in simple numbers, the null function f of x takes an input x and returns 0. No matter what x you put, it will always return 0. So there's no real importance of this function, but it's a special function, so I will mention it. There's another function. F of x returns a constant k, where for our purposes k is an element of the real numbers. K can of course be anything else, but in the book at least we are only talking about k being a real number. So this right here is what we call a constant function, because it is outputting a single constant no matter what the input of x is. No matter which x you put, it will always output that same constant. Note that f of x equals 0, the null function, is one particular case of the constant function when the constant happens to be 0. The next function we'll be talking about is the unit function, f of x equals 1. Again, there's nothing much to say here. The unit function is simply the function that outputs 1 for any input of x. Next, we'll talk about the identity function. This function is a little bit more important. The identity function produces the output as the input. The input you put is equal to the output you put, no matter what you do. So this is what we call the identity function. It is quite important. There's multiple types of identity functions, of course. One extremely simple one is just simply f of x equals x. Could also have variants of this, like saying x to the 1. You could even have f of x equals 1 times x. This is all the same thing. It's the function that gives you the input as the output. So this function is useful in that knowing about it, we can eliminate it or even bring it into existence. For example, f of x equals x times 2 divided by 2. There's nothing wrong here. This is also exactly identical to the identity function. So that means that multiplying by 2 and dividing by 2 does nothing. It's simply the same input is the output, which means we can cancel it out in equations. We do this all the time without even thinking about it. And then I'd like to talk about some other families of functions that we normally use in our common A-level activities. One simple function is the linear function. F of x equals, well, we can write it as, I'll just write it in this format, mx plus c. This is a straight line function. Another set of functions that we use are all the higher power functions. For example, f of x equals ax squared plus bx plus c. This function you would no doubt know as a quadratic function because it has a square term in it. The next function on this list would be this function, ax cubed plus bx squared plus cx plus d. This is a cubic function and we can keep going. We can add another term after this and get another highest order term. For all of these functions, this here a is not equal to 0, here also a not equal to 0, and here there's no real limitation that m not equal to 0, but generally if we are expressing a line, we would have some m. M can of course be 0 potentially, but a quadratic function should not have its a equal to 0, because then it would not be a quadratic function. If a was 0, this part would not exist and we would have a linear function. Similarly, if a was 0 here, this part would not exist and we would have a quadratic function. So we express the limitation that the highest order term's coefficient should not equal to 0. All of these functions after this point are what we call polynomial functions. Polynomial. They have multiple powers of x going from some number n all the way down to 0th power, and they don't have any negative powers. For example, f of x equals x squared plus x plus 1 over x would not be considered a polynomial function. Polynomials must have integer powers, positive integer powers, or including 0 of x's in some highest power down to 0th power. So any polynomial function should be of the form fx equals a n x to the n plus a n minus 1 x to the n minus 1. This a n minus 1 a n is just a constant a indexed at n. This is one special constant, this is another special constant, and I'm putting this number of a n minus 1 here just so that I can repeat it as many times as I want. If I put like here, if I put a here, if I put b here, then it would be inconvenient as then I don't know where I have to end. So we have a n x to the n, b plus a n minus 1 x to the n minus 1 plus a n minus 2 x to the n minus 2, so on, n minus 2, so on up to a2 x to the 2 plus a1 x to the 1 plus a0 x to the 0, which of course x to the 0 is 1. So we go all the way down to the constant term, and this is what we define as a polynomial function. And that concludes the lesson from today. We talked about a lot of things today. We talked about functions, relationships, how different functions behave, what their domain, range and codomain are, and then we discussed how special functions behave. For example, we discussed what the inverse function is, how an inverse function can be defined as the function that gives the input corresponding to a certain function of a certain output. We discussed the property that f of f inverse of x is equal to x, and f inverse of fx should also be equal to x for a proper inverse function. We discussed that a proper inverse function can only exist if the function itself is 1 to and 1 to 1. We discussed how when you don't have a proper inverse function, you can still define some form of inverse function that only works for certain values. We then discussed composite functions, which are functions that take one function's output and plug it as another function's input. And finally, as a final measure, we discussed certain special types of functions that we talk about in the local A-level syllabus. Thank you for watching and goodbye.